Voyager 1 has traveled over 166 times farther from the Sun than Earth, sending back streams of data no human has ever touched. But when NASA's quantum AI ran those signals, it flagged something unexpected. A pattern that seemed to align with the path of 3/Atlas, only the third known interstellar object to sweep through our solar system. A spacecraft launched in the Cold War, a cutting-edge quantum algorithm, and a visitor from another star now tangled in a single anomaly. If this flagged correlation holds, it could rewrite what we know about cosmic visitors and our own reach into deep space. But why would an interstellar object leave any fingerprint out beyond Pluto? The explanation might be stranger and more profound than anyone imagined. Something in the Voyager 1 data stream caught the quantum AI's attention. Not a glitch, not a random spike, but a pulse timed with uncanny precision. The flagged pattern didn't match any known solar event. It didn't line up with cosmic ray storms or the usual plasma wave bursts that Voyager's instruments have tracked for decades. Instead, the anomaly tracked a path that when mapped overlapped the projected trajectory of 3/A as it swept through the outer solar system. The AI didn't just spot a blip. It registered a sequence, a rhythm in the plasma wave data, and a subtle shift in the cosmic ray background. Each signature fell within the same narrow window, separated by just hours from the modeled passage of 3/8 past the helipause boundary. Engineers at NASA's Jet Propulsion Laboratory double-checked the raw telemetry. The data wasn't corrupted. The instruments were functioning within normal parameters. The quantum algorithm had flagged a timing overlap that no previous analysis had surfaced. It wasn't just a single data point but a cluster. A rise in electron density, a faint oscillation in the plasma wave spectrum, and a brief uptick in high-energy particle counts. The pattern didn't match previous coronal mass ejections or background turbulence. It was new, at least as far as anyone could tell from nearly 50 years of Voyager records. What made this alert different was the context. Voyager 1, now over 166 astronomical units from the Sun, was sampling the plasma environment far beyond the planets. 3E/ATL, the third interstellar object ever detected, was on a trajectory that by chance placed it roughly in the same sector of the sky during the flagged interval. The AI's model calculated the probability of such an overlap by random chance at less than 1 in 10,000 given the timing and the directionality of the signals. No one could say for certain what caused the anomaly, but the flagged window opened a new question. Could an interstellar object moving at 61 kilometers per second leave a detectable signature in the plasma environment, even at distances well beyond Pluto? The quantum AI didn't offer explanations. It only surfaced the pattern and the timing. The rest was left to human curiosity and to the possibility that something about these cosmic visitors is written into the very fabric of interstellar space. The implications, if real, could ripple through everything we know about how our solar system senses the outside universe. And for the first time, Voyager's ancient instruments might be catching a whisper from something truly alien passing by. Voyager 1 is now more than 166 times farther from the Sun than Earth, pushing through a region no other spacecraft has reached. Every byte coming back is a direct sample of the space between stars. That data isn't just numbers on a screen. It's our only window into the raw, unfiltered environment and beyond the solar system's edge. When a new pattern appears, especially one that lines up with the path of an interstellar visitor, it raises questions that go far beyond academic curiosity. For scientists, the chance to spot a signature from something like 3/Atlas is a once-in-a-generation opportunity. Interstellar objects are rare. Before 2017, not a single one had ever been tracked in our solar system. Now, with Voyager 1's detectors still running after nearly 5 decades, there's a slim but real chance to catch the faint imprint of a traveler from another star. The spacecraft's plasma wave instrument, cosmic ray counters, and magnetometer aren't just collecting background noise. They're recording the subtle fingerprints of the universe itself. If a passing object stirs the plasma or nudges the magnetic field, Voyager is the only outpost that might notice. The stakes aren't just scientific. Every flagged anomaly is a test of our ability to recognize the unexpected. If Voyager's data can reveal that interstellar objects leave a detectable trail, it could change how future missions are designed. Imagine probes equipped to watch for these signatures or early warning systems that use deep space sensors to alert astronomers to new arrivals. The implications stretch from basic physics, how objects interact with the interstellar medium, to practical questions about how we might one day intercept or study these cosmic messengers up close. For the broader science community, this isn't just about confirming a theory. It's about expanding the limits of what we can observe and proving that even a 47-year-old spacecraft can still surprise us. When a quantum AI flags a pattern that lines up with the path of a true interstellar visitor, it's not just a technical achievement. It's a reminder that the universe is still full of unknowns waiting to be decoded. That's why every flagged signal matters. Each one could be the first hint of a new way to sense the cosmos. Raw data from Voyager 1's plasma wave and cosmic ray instruments arrives as a stream of numbers. Electric field voltages, particle counts, narrowband frequency spikes. But in late 2025, the quantum AI flagged something that stood out from decades of routine. First, it picked up a directional shift in the cosmic ray background. The change wasn't dramatic, just a subtle skew in the arrival angles of high-energy particles lasting less than 8 hours. The shift lined up almost to the hour with the predicted passage of 32/Atlas through a zone about 0.3 astronomical units from Voyager's position. That's roughly 45 million kilometers, a cosmic stone's throw at these distances. The flag pattern didn't fit any known solar activity. No coronal mass ejection, no shock wave from a distant flare, and nothing matching the usual periodicities in galactic cosmic rays. The particle counts rose by about 3% then faded back to baseline. For context, cosmic ray flux near Voyager has been remarkably stable since it left the helipause in 2012 with only slow seasonal undulations as the spacecraft drifts deeper into interstellar space. A spike of this timing and shape is rare. In the plasma wave dataset, the AI registered a faint narrow-band oscillation, a blip at 2.9 kHz. The signal lasted just under 2 hours, buried in the noise, but repeated averaging pulled it above the detection threshold. The frequency matched the electron density expected for Voyager's location, but the amplitude was higher than background by about 20%. The timing overlapped with the cosmic ray skew, both peaking within the same 6-hour window. The AI's model calculated the odds of such a double coincidence given the 50-year archive at less than 1 in 10,000. Engineers at JPL checked for instrument artifacts, temperature drifts, power fluctuations, memory errors. None matched the anomaly window. The spacecraft's attitude control logs showed no thruster firings or orientation changes. Telemetry was clean. The flagged signals didn't match any previously cataloged instrument glitches or deep space network transmission errors. The quantum AI's criteria were simple. Look for patterns that align in time, direction, and magnitude, but don't fit known solar, galactic, or spacecraft-caused events. It flagged the cosmic ray skew and plasma wave blip because both lined up with the modeled path of 3I/loss and both appeared in a time window when nothing else in the archive looked similar. The flagged window was narrow, just hours out of decades of data. The signals were faint, but the overlap was enough to trigger the alert. The data team knew better than to jump to conclusions. Cosmic ray backgrounds can fluctuate for reasons no one fully understands. Plasma waves in interstellar space are still a frontier with turbulence and density gradients producing all kinds of surprises. But the flagged anomalies raised a real question. Could a fast-moving interstellar object, even at a distance of tens of millions of kilometers, leave a detectable imprint in the plasma or particle environment? Or was this just a coincidence, a statistical ghost in a sea of random noise? The flagged patterns didn't answer that question. They only showed that for a brief interval Voyager's ancient detectors caught something that lined up with the path of a visitor from another star. The next step would be to ask what kind of physical process, if any, could connect the passage of 3I/Atlas to a whisper in the plasma and a bump in the cosmic rays billions of miles from home. A 100-meter object hurtling through the interstellar medium at 60 kilometers per second might seem too small to matter, but plasma physics tells a different story. In space, even a modest traveler can disturb the magnetic fields and charged particles that fill the void. The concept is called magnetic draping. When a fast-moving object plows through a magnetized plasma, it can compress and bend the field lines around its leading edge, forming a sheath, a kind of invisible bow wave. This effect is well documented on planetary scales. Venus, for example, has no global magnetic field of its own, but the solar wind drapes the sun's magnetic field around it, creating a distinct boundary. The same physics scaled down could apply to any unmagnetized object moving fast enough through a plasma, even a comet or asteroid from another star. The helipause, where Voyager 1 now drifts, is a prime example. There, the interstellar magnetic field doesn't just stop at the edge. It bends and wraps, forming a sheath hundreds of astronomical units across. Voyager's instruments have picked up the signature of this draping, a persistent, slightly stronger field and a subtle rotation in direction. The sheath acts like a cosmic traffic sign marking the transition from solar to galactic influence. If a passing object like 3I/loss crossed this region, it would face the same physics though on a much smaller scale. But here's where the theory gets tricky. The interstellar medium is thin, just a fraction of a particle per cubic cm, and its magnetic field is weak, around 5 micro-G. For a 100 m object, the region of influence would be tiny, perhaps a few km across. The wake it leaves behind would be a threat, not a river. Yet, Voyager's plasma wave instrument is sensitive enough to register changes in electron density and narrow-band oscillations, even when the signals are buried in noise. In 2017, the spacecraft detected a faint, persistent hum from the interstellar plasma. Evidence that even small fluctuations can be teased out with enough patience and averaging. Some theorists suggest that a fast interstellar object could carve out a wake in the plasma, creating a trail of compressed and redirected field lines. The effect would be fleeting. A rise in electron density, a blip in wave frequency, maybe a brief skew in the direction of incoming cosmic rays. On planetary scales, these wakes can extend for thousands of kilometers. For a comet or asteroid, the disturbance might persist for minutes or hours as the plasma relaxes. The odds of Voyager being in the right place at the right time are slim but not zero. The spacecraft's detectors are always on, always listening. The analogy to the helipause draping isn't perfect, but it's the best model available. Both involve a moving obstacle, a flowing plasma, and a magnetic field forced to bend and pile up. The difference is scale and, crucially, detection. To catch such a whisper, Voyager's instruments need to be sensitive not just to the obvious, but to the improbable. A spike in density, a shift in wave amplitude, a momentary twist in the field. Quantum AI trained to recognize patterns invisible to the human eye flagged the timing overlap between Voyager's anomaly and 3/Atlas's passage. It didn't explain the physics, but it raised the possibility that even a cosmic pebble could leave a mark in the plasma sea. This raises the hypothesis that interstellar visitors, no matter how small, might write their presence into the fabric of space, if only for a moment. The draping effect observed at the edge of the solar system could have its miniature counterpart wherever fast-moving objects cross magnetic fields. For scientists, this is both a challenge and an invitation to rethink what counts as a detectable event and to consider that the universe's faintest signals might be the most revealing. If Voyager's data can capture the echo of a passing interstellar object, it could redefine the boundaries of what deep space exploration can sense. The prospect inspires awe and a sense that our instruments, however old, are still tuned to the unknown. Voyager 1, still pushing through the darkness beyond the edge of our solar system, keeps sending back data nobody else can. Its detectors are tuned to the faintest tremors in the plasma, the smallest shifts in the cosmic ray background, and the subtlest twists in the magnetic field. These are not just numbers. They are the only direct signals we have from interstellar space. When a quantum AI flagged a pattern in that data, one that lined up almost hour for hour with the predicted path of 3/AT, something changed. This was not a routine blip or a glitch that could be written off as noise. It was a sequence, a set of signatures that echoed the passage of an object from another star. The odds of that timing being random, less than 1 in 10,000. That is the kind of coincidence that forces a second look. The flagged window did not come with answers. It came with a question. Could a visitor from deep space actually leave a mark in the plasma even at these distances? The quantum AI did not explain. It just surfaced the pattern, then left the rest to human curiosity. That is where the real puzzle sits. Voyager's old instruments might have caught a signature from a traveler that started its journey millions of years ago, long before Earth had cities or even mammals. If so, it is a reminder that the universe still has ways to surprise us, even with tools we built half a century ago. That is why this connection matters. The flag signals are not just a technical anomaly. They are a test of what we are able to notice, of how we interpret the rarest events, and of whether we are ready to see the universe as it really is. Each bite from Voyager 1 is a chance to catch something new, something that could change the way we think about the space between stars. The next step is clear. Test the roadmap, dig deeper, and see if the pattern holds when the data is stretched and stressed from every angle. Quantum AI flagged the pattern, but the next step is all about pressure testing the roadmap. Every flagged anomaly gets a second and third look. The first challenge, instrument noise. Voyager 1's detectors are nearly 5 decades old. The plasma wave system, for example, is sensitive enough to pick up faint hums from the interstellar medium, but it's also vulnerable to thermal drift, cosmic ray hits, and even memory glitches from deep space radiation. Engineers at JPL and independent teams at the University of Iowa and Caltech run their own checks, sifting through raw telemetry to rule out false positives. That's the standard. No single alert stands on its own. Oversight bodies, including NASA's Deep Space Network and the Minor Planet Center, review the flagged intervals. They compare Voyager's event logs with ground-based tracking of 32/ALS. If a spike lines up, it's logged for further analysis. If it doesn't, it gets tossed into the archive. The process is slow, methodical, and designed to catch mistakes before they spiral into headlines. Risks are everywhere. Instrument artifacts can mimic real physics. Cosmic rays can trigger blips that look like signatures. Even data compression algorithms tuned for ancient hardware can introduce patterns that only exist in the downlink. The quantum AI is powerful, but it's not immune to p-hacking or overfitting. That's why every flagged window gets reanalyzed using different algorithms and fresh statistical models. If the pattern holds up, it moves to the next round. This isn't just about confirming a signal. It's about making sure the result can be falsified. If Voyager 2, drifting through a different patch of interstellar space, doesn't see the same anomaly under similar conditions, the whole theory takes a hit. The broader research teams keep their skepticism sharp. They know that a single coincidence, no matter how improbable, doesn't rewrite the textbooks. But if the pattern survives every test, it opens the door to new possibilities. The roadmap is clear. Keep the data flowing, keep the checks rigorous, and stay ready for whatever the next anomaly brings. In 2025, astronomers confirmed 32/Atlas as only the third known interstellar object to cross our solar system. Decades earlier, Voyager 1 began its journey, now sending data from over 166 astronomical units away. When that data was run through NASA's quantum AI tools, the system flagged a timing overlap, an anomaly in Voyager's cosmic ray and plasma readings that coincided with the projected path of 3I/loss. The flagged patterns do not prove a direct interaction. Instead, they raise new questions about how interstellar objects might subtly influence the space around them, even at vast distances. While analysis continues, most of the underlying Voyager datasets remain publicly available through NASA archives. Yet, the true nature of the flagged correlation remains uncertain. No official document has confirmed or denied a physical link. For now, the evidence highlights both the power and limits of advanced data analysis. The mystery of what Voyager 1 detected, if anything, remains open, reminding us that each new discovery can challenge the boundaries of our knowledge.